Let's just think about something like the equations of motion. Everybody knows F equals ma, right? F is equal to ma. I can write that. This is now, let's say, in one-dimensional form. Okay, this is what it looks like if I just have a thing and it's constrained on, it's sliding on a surface, right? But what if we want to generalize that to multiple dimensions? I have a couple of options. I can write fx is equal to max, fy is equal to may, fz is equal to maz. I can do that. Or I can introduce more powerful notation. And I can say, well, there's this thing called a vector. And I can write that using a much more succinct notation. This is pleasing to my mind because it's the same symbols. I need to remember less, right? It also allows me to manipulate those symbols without separately thinking about each one of those components. And as long as I have a nice, consistent set of algebraic rules that make the manipulations work the right way, it also has a number of rules, but I have less opportunity for error because I'm not individually manipulating each one of these equations. So let's say the moral of the story that I'm trying to tell right now is that you should be eager to use the biggest symbols that you can. When I say big symbols in this context, I mean that something like ax is a subcomponent of the a vector. And what I mean by that ax is a small symbol and a is a big symbol because it contains these other symbols, right? And by using big symbols, you're able to think bigger thoughts. Does that make sense to everybody? It's like, it is crazy. It's the wonder of notation. Because those are only 3 symbols now. It's doing the same stuff as 9 symbols on the left-hand side. And if I do operations on that, I'm simultaneously doing those operations. Now, whether I'm doing that in my mind, or whether I'm doing that on paper, or whether I'm doing that using programming code, the idea is the same in all cases. I'm using less symbols to represent that big idea. And so I can just tell you that when I kind of clicked programming, this is one of the things that you click in programming is, oh, if I make big symbols, I can think big thoughts. And I can see things in my program. I can think about my program much more easily if I have big symbols, which means that I have few symbols. And that's part of it is just none of us have the ability to memorize all of the things in your program. But most of us have the ability to memorize in this other weird way where I'm linking. I'm saying, oh, this function does this thing, like the Pretoria area code, right? And you may think, oh, but it's more work. It's more work because I'm like, not only am I writing the actual code, but I'm also writing all these extra stuff that like makes the symbols. But no, the amazing thing is like by making those symbols, you think bigger thoughts and you remember things better and you think better about problem-solving scenarios. So that's the intro to the idea that you should be really eagerly using vectors and matrices in almost every place where you can, especially when you are doing this with the aid of a computer. So let's see how this idea plays out in a couple of different ways. In the multivariable world, it's obvious. We are automatically working with vectors and matrices. But if you think about writing down the equations that govern the behavior of a system where we have maybe 5 inputs or 10 outputs, everybody hopefully would run out of patience before writing down, I don't know, what's 5 times 10? 50 transfer functions, right? Like all manually developing 50 transfer functions. So I wouldn't call on you to do that by hand. But everything we say about systems in this form generalized to an arbitrary number of inputs and outputs. So if we're talking about something like matrices or transfer function matrices, you're going to get the best mileage out of manipulating those matrices if they have numeric coefficients by using the control library. Why? Because the control library will allow you to manipulate those systems. It will also allow you to obtain step responses and other kinds of systems, in other words, converting between transfer functions and state space representations, all built into that one object. You can multiply these, you can add them, you can do all kinds of stuff with them, and if you have it in one form, you can convert to the other forms. If you have numeric coefficients, if you're trying to convert from one representation to another, it is by far the easiest way, and definitely my recommended way, to convert between representations just using the built-in functions. It's less error prone, it's probably it's nicer in 1,000 different ways. Avoid very rapidly translating the vector matrix equations to sets of normal equations and then going from there. Please try to be eager in applying matrices and vectors. I'll show you kind of a common version of the problem now. So we had two equations, and the one had a product term and the one had a normal term. And one way of approaching this problem is, as I've mentioned in a previous video, to just kind of imagine that xy is a separate variable, linearize that separately. I'm just going to take a slightly different approach here, which is that I can, by now most of you should be able to intuitively understand that after linearization, that's going to end up being an equation that looks on the left-hand side, forget about the right-hand side, looks on the left-hand side like this. Now, one way to proceed from here, knowing that there's a dx and a dy in the model, is to solve those equations by substitution. So one way to look at these equations is to say, oh, wait, the problem here is I have two things on the left-hand side, and I only want one thing on the left-hand side, and I'm looking for maybe an equation that has dx dt in the first line and dy dt in the second line. And so one way of doing that is just substituting that in there and then doing lots of algebra to kind of work through and move all the stuff to the right-hand side and so on. Another way of doing this using the lens of eagerly applying linear algebra concepts is to recognize that that problem can be rewritten in a vector matrix form as this form. Everybody see what has happened here? So those are equivalent equations. I've just used vector matrix notation in the first case, or in the second case, and I've used the normal scalar notation in the second case. Now, while it is absolutely true that perhaps in this particular case with just the two equations, you end up winning by doing the simple substitution and running through the rest of the algebra by hand. Imagine generalizing this general case, because you can imagine that we have state space models where we may have 10 states, right? If I came across a system like that, and there were many product terms, I would run out of time if I were manually solving those equations. But the identification of the coefficients of the derivative vector is a much more mechanical process and scales significantly better. In other words, it's not much slower to do this if there were 10 of those equations than, when I say much slower, it's not slower in the same kind of way that solving those equations is slower. So if you solve this exact same problem but with 5 or 6 or 7 derivative variables, you start really paying a big price. Now, how is this actually useful in your life? I will give you full marks if you got until this point and you told me, well, let's call this thing x, And then I would just write this as x. That solution, if you had stopped there, full marks. So part of the reason why you are biasing away from this stuff is like you're very focused on getting the answer. I want to change the conversation to make sure that you are thinking big thoughts and using large symbols. So I want to award you or reward you by solving the problem in this way, because what's left? Multiplying out the matrices and gathering the coefficients and stuff. Like, I want to be giving you marks for knowing what the state space representation is in the first place. Right? Knowing why we would want it, knowing that this kind of strategy would be a successful strategy. The computer can do that in milliseconds. I would like you to kind of multiply that out in the sense of being able to identify whatever that coefficient matrix is of the x, y vector. And I would like you to kind of tell me that you know that this is A. But that's good enough. I almost never want, or let's say the key thing about a problem is almost never the answer for me. Or let's say the numeric value of all the coefficients. Okay, so that's one way in which you benefit from this idea, right? So this idea that you can make these big symbols, you can group them all together, and you can do these operations without doing them. Without manually going through the motions of doing them, you have notation that shows me that you know what you would be doing if you had time to do it, or the kind of code that you would have to write to solve that kind of problem.